the main idea here is that the present is affected not only by the past, but also by things that come back from the future. And the uncertainty is necessary to allow this to happen without violating causality, or with still giving us the possibility of free will to decide what we will do in the future, and nevertheless the future still affects the present. So this is a very surprising result, and it's a very deep idea that explains why does nature behave in a capricious way, in a semi-capricious way. So let me start, and I will start with a paradox. I like to start always every new research with a paradox. I wrote a book together with a collaborator that's called Quantum Paradoxes, and I, of course, recommend it very highly to all of you because I think it's a very interesting book. So here's a paradox that led to this new way of looking at quantum mechanics. Let this be time, and I have two particles, one here and one here. They are sitting still, and they have spin half, each one of them has a spin a half spin variable, and these two spins were prepared in the famous Einstein-Podolsky-Rosen correlation, meaning that sigma 1 for the first particle plus sigma 2 for the second particle is equal to 0. That means that in every direction, there is a correlation between their components. If I measure the component in the x direction of the first one and find it to be equal to +1 in this normalization, then sigma 2 will be -1 in every direction. This is the famous EPR state, or Einstein-Podolsky-Rosen, that led to Bell's formulas, led to whole new ideas about non-locality in quantum mechanics. But that's not the thing that we are interested in now. So here is the world line of particle 1, and here is the world line of particle 2, because they are sitting still. And sometime here, this was the initial time, t0. Now at some time here, t1, I measure the spin of this particle in the x direction and find that sigma yx is equal to +1. Sigma 1x is equal to +1. The spin in the x direction is equal to +1. According to the interpretation, the conventional interpretation of quantum mechanics, what I have to do after I've done this measurement is to replace the original vector of Hilbert space with a new vector that tells me that from now on, sigma x1, it will be equal to +1. This is a vector in Hilbert space that will continue from now on to be equal to the statement that I know that if I will measure again sigma 1x, I will find equal to +1. But I also have to do something here, because I know that the sum of the two of them is equal to 0. I know that I have to replace the particle here by a new state of sigma 2x equal to -1, because the sum of the two is equal to 0. But I have now a problem, because if I were in non-relativistic theory, there would be no difficulty knowing when I have to do this replacement. But I'm in a relativistic theory. You know that if I go to a frame that moves relative to this frame, the equal time will be this line. That means that for a new Lorentz observer, you will have to say, I have to replace already here sigma 2x by the value -1, because this is the equal time for him. So he says, if I measure here and find it +1, then in my frame, I have to say that already here, sigma 2 is equal to -1. But then I come back to the original frame and say, if he's right, then I take my frame and say, this is equal time. Already here, sigma 1x has to be equal to +1. But that's before the time that I have made the experiment. So it doesn't make sense. You see, this is a paradox. Now, how do you solve this paradox? There are two ways to do it. One way is to say, look, you're not talking about actual measurement. If you would do actual measurement, everything will be fine. You could calculate the probabilities in every frame that you like. You're talking here about a story about the collapses that we are not interested in because we are only interested in results for real experiment. This is one approach. The other approach is to say, no, I want to believe that there is a real reality here, also described by these vectors, and therefore, if this story tells me that already here, sigma 1x was equal to plus 1 before the measurement, maybe quantum mechanics is trying to tell us that when we do a collapse, it affects not only the future, but also it goes backwards in time. So this is the hint. And I want to show you now that you can actually do this correctly, in the sense that you will keep the same prediction, but it will open completely new way to think about quantum mechanics. So here's the idea. By the way, stop me at any time that you want to ask questions. If I'm going too fast or if something you don't understand, don't hesitate to stop me. So far, you understood everything? No question? Good. Here's the brave man. Yes. Okay.
I don't understand your statement about sigma 1 plus sigma 2.
About what? Sigma 1x?
Yeah, I don't understand.
Okay.
Those,
good.
They don't have any zero.
I was looking for some challenge. Okay, look. I make the measurement here, sigma 1x equal to plus 1.
No, the very first statement.
Huh?
What does it mean that sigma 1 plus sigma 2 is 0?
That is the...
On the right. Yeah, that.
This thing?
Yeah.
Okay, this is the so-called Einstein-Podolsky-Rosen state. Suppose I have a molecule with 2 atoms, and the total state of the spin is equal to 0. It's an S state. Now, it's split into 2 atoms, one going this way and the other going that way. Then I know that because all the components of the spin are conserved, sigma 1x plus sigma 2x equal to 0, sigma 1y, okay?
Yeah.
So this is the so-called Einstein-Podolsky-Rosen state because I have components in 3 directions that don't commute and still they know about each other. Sure. That was a big surprise that was discovered by this, and both tried to work very hard to show that it's not inconsistent. Okay, that's a big story. I don't want to go into that. Yes, but all right. The next step, you understand the paradox. Okay.
Yeah.
Yes.
And I'm sort of geometrically and relativistically challenged, so I didn't understand quite what was the transformation that had you comparing 2 different times.
No, I'm just saying, if I do here,
you do that
this time there is no problem.
Right.
But about this time, when do I have to replace this by sigma 2?
Yeah.
This is simultaneity. Simultaneity is not invariant under relativistic transformation, special relativity. In special relativity, 2 things that equal at each time depend in which frame you're looking, right? So if I go to another frame that moves relative to the first one, then this will be, at this point here, will be the equal time to this point.
It's a Lorentz transformation.
Huh? This is Lorentz transformation. In Lorentz transformation, look, in Lorentz transformation in 1 dimension, t and x, this is the equal time for one observer. The equal time for another observer is this one.
So it's some observer who's looking at that from a moving frame.
Yeah, looking at this experiment from a moving frame, and the moving frame observer will say, this is my equal time, and therefore I have to replace sigma 2 here, on this point. Then I come back to the first frame and say, if you replace it here, and also here, in my frame, the sum was equal to 0, then this must be already equal to -1 to +1 even before I did the experiment. So this is the paradox. Now I want to show that quantum mechanics actually tell us that we can do this in a new way, and this is the beginning of the whole new approach. Okay? Any other questions? Don't be hesitate. Don't hesitate. Oh, good. I see some hands now. I'm beginning to be happy. Otherwise, I will fall asleep if you don't ask questions. Yes.
So why can't we solve the paradox?
But you have to talk louder.
Why can't we solve the paradox by saying that the state vector really expresses some subjective knowledge of the observer about the state? And if we fix the observer, then we also fix the reference frame.
Okay, I simply could not hear even one word. Could somebody tell me more loudly what is that? You know?
Okay.
Anyone?
I can try to speak up.
So maybe you should stand up,
and stand up and yell, okay?
So I would like to ask why we can't just say that the state vector expresses just subjective knowledge of an observer about the state, or about the particles. So if we fix the observer, then we also fix the reference frame, and we also fix the time at which the other part.
Okay, you're right. There could be many different interpretations, but if we believe that the wave function is something real, okay, that doesn't depend only on the knowledge, but it's a real description, then what I'm saying is correct. So, look, if I did not have any other way to prove what I'm going to say, then of course you are right, I should defend it more. But since this is just a hint, and I'm going now to show you by formalism that I can do that, so don't worry about the interpretation, okay? It's just a hint. The hint is if wave function is really something real, then it should be invariant under Lorentz transformation. If it's only a question of knowledge, then of course it may depend on the frame. So it's an issue whether a wave function is just an issue of knowledge or it's a true property of the particle. If it's a true property of the particle, then we have to speak about it covariantly. If it's a function of the knowledge only, then of course it may depend on who has the knowledge. All right? So I took the hint from the fact that I believe that it's real, and that led me to something interesting. And the fact that it led me to something interesting means that indeed it's better to think about the wave function as real, because that is the proof of the pudding, okay? Yes?
Yeah, at this stage you incorporate relativistic version of quantum mechanics, but these power
only special relativity. So in special,
it's only from that point of view. But,
I know. Again, look, I don't want to go too deeply into that. Since it just was a hint, I'm going back to non-relativistic quantum mechanics and going to show that the hint was right. Okay? So don't worry. You're right that if I go to special relativity, I have to think about the Dirac equation. But this was just a hint. Okay? And for that part of the hint, the non-relativistic picture was correct. Any other questions? Okay, so here comes the new idea that came out from that. And let's see if it's going to work. Beautiful. That's the best. Whoa! My God, that was close, right? Okay. So I want now to speak about something that allows me to do a pre- and post-selection on a quantum system. To understand what I'm talking about, I want you to think about this type of experiment. That's called exclusive experiment, exclusive from excluding. You see, suppose I have here a cloud chamber. How do you spell cloud?
O-U-D.
O-U-D? A cloud chamber. A cloud chamber that was used when I was a student, it was very much to see cosmic rays. Now it's not used so much, but anyhow, it's a chamber that has a superheated gas here, so that when particle goes through, it leaves droplets. And so you can see the orbit of the particle by the droplet that it leaves. So suppose I send many particles, one after the other, through this cloud chamber. Each particle leaves some cloud. The first particle leaves this steps, the second one leaves this one, etc. Now each particle comes out. Some of them come out in this direction, some of them in this direction, some of them in this direction. Suppose I put here a counter, and I then go back. I took all the pictures, but I'm going to exclude all the pictures that came from the other particle and keep up only the pictures that were connected with this particle. So this is a pre-selection, and this is a post-selection. And I'm going to look only on the tracks that were left by particles that were pre-selected and post-selected. Now, very, very important. I could not do this experiment in classical theory. Why? Because in classical theory, if I have two particles that are described by exactly the same initial state, they will both go in the same line, and they will therefore both of them end in the same final state. Because in classical theory, if I know the state at an initial time, and I have the same surrounding, I will always end up with the same state finally. But in quantum mechanics, the meaning of the uncertainty principle is that even though all the particles here started in the same state, some of them ended here, and some of them ended here, and some of them ended here. So I can ask for the sub-ensemble of those that started here and ended here, what were their properties in the present. Okay, so this is the idea of pre- and post-selection of ensembles, pre- and post-selected ensembles. Very important. Something that only quantum mechanics allows us to do. And I'm going to claim that this is the real gain of the uncertainty principle, that it allows us to do this kind of selection, because it will open a completely new host of phenomena if we know how to look for this kind of sub-ensemble, pre- and post-selected ensemble. Okay? So let's now see what is the new formalism. So I'm interested in the following question. This is time t. At some initial time t1, I started with my particles, or with all the particles in the same state psi 1. So each one of them evolves with the same Hamiltonian as psi 1 of t. All the particles in the ensemble, I'm going to consider the ensemble of many particles, all of them started in the same state psi 1 and evolved with the influence of the same Hamiltonian, the same time evolution as a function of t. At some intermediate time here, t intermediate, I am making a measurement of an observable that is described by an Hermitian operator A that has a complete set of eigenstates, A times a complete set of states AN is equal to AN times AN. This is the eigenvalue, and this is the eigenvector of the state A. I hope that you are all familiar with this notation, right? Anyone here is not familiar with this? Okay. So, I will get here, for a particular particle, I will get here some answer, which will be a particular AM. So, I have to replace the initial state psi 1 by a new state AM. This new state continues to evolve as AM of t. Now t goes from this intermediate time on. At time t2, I do a post-selection at a state psi 2. I post-select a state psi 2 for the particle. And the question that I'm asking is, knowing psi 1 and knowing psi 2, what is the probability to get an intermediate state AM here? Okay? So this is pre-selection, post-selection, an experiment in the middle, and I'm asking for this pre and post-selection, what is the probability to get a particular answer here? And it's very simple to do the calculation. I take the initial state psi 1, evolve it in time from the time t1 to the time t. This is the time evolution. You know, the time evolution ut1 is equal to e to the minus I, the Hamiltonian, times t minus t1. So this is the time evolution of the initial state. I time evolve it until the intermediate time t. Then I project on the state AM. This gives me the amplitude to start with psi 1 at time t1 and end up with the state AM at time t. Then I start with this new state, because I know that I get that particular state from now on, evolve it in time from the intermediate time t to the final time t2, and project it on the state psi 2. And this whole thing gives me an amplitude, Cm. This amplitude, absolute value square, gives me the probability to start with psi 1, in the middle getting the answer Am, and finally get the state psi 2, right? Okay. This is the usual picture. Now I'm doing something that mathematically is completely trivial. Yes, you have a question?
Can I just clarify? This psi 2, you mean there's a measurement made at...
Say it again?
By psi 2, you mean there's a measurement made at t2,
yeah.
and the result corresponds to the projector?
At time t2, I start with the whole ensemble, go through this set of experiments. Time t2, I do an experiment where I measure something that this could be one of the outcomes. This is like the post-reaction, and I only keep those particles that ended up in that thing. Like I showed in this cloud chamber, I only collect the particles that gave me that direction. So here I only collect particles that start psi 1 and ended up at psi 2. It's a sub-ensemble. It's not the whole ensemble. So if I add up all the Cm square, I will not get 1, because I will get only the sub-ensemble. So I have to normalize the Cm square by the sum of them to get only the properties of their sum. Okay? All right. Now I do something that is absolutely trivial mathematically, but it will be very, very significant physically. unbelievably significant. It will open completely new way to think about quantum mechanics. Sometimes extremely trivial mathematical things could open completely new doors. What do? I simply take this U and bring it here. So I will have here U dagger of T2 T times psi 2 AM U times psi 1. And it gives me exactly the same CM. So look, the only thing I've done is put this one here, and I have now U dagger psi 2, AM, U psi 1. Now what is U dagger psi 2? U dagger, if U is e to the minus IHT, then U dagger is e to the plus IHT. But this can be rewritten as e to the minus IH times minus T. So U dagger is the thing that replaces T by minus T. It takes you back from the future. It goes back in the opposite direction. So this new picture is very, very interesting. It tells you that quantum mechanics tells you that it's okay to calculate all the properties in the present for any experiment in pre- and postulated ensemble in the following way. This is C. I start here with the state psi 1, involve it to any time in the present as psi 1 of T, end up with psi 2, evolve it back in time. In fact, when I evolve it back in time, I have to take it as a bra instead of a cat. I involve psi 2 of T back in time, and I calculate anything that I want in the present on equal footing with the two vectors. So quantum mechanics tells me it's okay. It's okay if you know that you're only going to use these two boundary conditions. It's okay to think about the whole present between the two times as being, in some sense, this being a description by two vectors. One of them going in this way, and the other of them going this way. One coming back from the future, and the other coming from the past. And I calculate all the properties in the middle using both vectors on equal footing. This is a new description, and the question is whether this new description leads you to some really exciting new aspects of quantum mechanics that you have not thought about before. And that's really what I want to show you. I want to show you that just starting to look in this way led to a completely new host of phenomena that's now being checked in many, many different places. One of them, by the way, here, very close in Toronto by Ephraim Steinberg, that made an interesting experiment, but it's all over the world. In China, Japan, Australia, South America, Europe, many, many places, USA, of course. Okay, so let's see what kind of new things I get from thinking in this new way. So, okay, let's start with the simplest quantum system we can think about. Spin-half particle with no Hamiltonian. It's the simplest quantum system that exists, and even there we will see something new. So here is time. At time t1, I have my spin-half particle found in the state sigma x equal to +1. That means that the spin is Sx is equal to 1/2 h bar. It's simply the Pauli normalization. But that means that the spin half in this direction is equal to 1/2 h bar. But I will use this normalization, call it sigma x equal to +1. That is the initial state. And the final state, I postulate only particles that end up at the state sigma y equal to +1. So in the old picture, you will say, okay, here I had just one vector, which is sigma x equal to plus 1. That's the whole story. And from now on, I will have another vector. Nothing interesting at all. Right? The new picture says, no, actually here there's two vectors. One of them going this way, which is sigma x equal to plus 1. And the other one going this way, which is sigma y equal to plus 1. And both vectors are alive here. Both vectors exist here. It's a new description. In this new description, actually, I'm allowed to say that sigma x is known and also sigma y is known. Something that, of course, in the case of one vector, I could never say. The question is now, how do I check it? How do I see that the fact that both sigma x and sigma y equal to plus 1? And it's not trivial. If I would measure sigma x, only sigma x, then of course I will get plus 1 because sigma x Hamilton is equal to 0, sigma x is conserved, so if it started to be equal to plus 1, at any time here I will find it to be equal to plus 1. No surprise at all. On the other hand, if I would measure sigma y, then of course I can get either plus 1 or minus 1. But I'm going to keep only the cases when I got at the end plus 1, so of course I will get in the middle for this sub-ensemble sigma y equals to plus 1. But that's trivial, that's not interesting, right? Because I'm throwing away the other one, so what's the big deal here? So far, nothing is interesting. Then I thought, when I first started to think about it, ask myself, what will happen if I will measure a new variable, which is sigma x plus sigma y? Not sigma x alone, not sigma y alone, but I measure sigma x plus sigma y. So if I trivially believe that sigma x is equal to plus 1 and sigma y is equal to plus 1, that maybe I should get it the answer 2. All right? Yes, if the picture is right, and both sigma x is equal to plus 1 and sigma y is equal to plus 1, maybe the sum of them should be equal to 2. But then the minute you look at it, you say, but that's stupid, it's impossible. Because if I look at sigma x plus sigma y divided by square root of 2, that is just a spin component in the 45 degrees. This is sigma x cosine 45, which is 1 of square root of 2, plus sigma y. This is just a spin component. A spin component can be only 1 or minus 1. It can never be square root of 2. So how can I get the square root of 2? So at first, when I thought about it, I said, oh my God, that picture cannot be right. Any questions so far? No? Everything is clear? Yes? Okay. So what do you think? Will I get the answer square root of 2 with some experiment or not? What do you think? That's a possible value. If I'm going to show you there will be an experiment that will give us this answer, sigma x plus sigma y is equal to 2, you will agree that there is something new here, right? Because it's impossible to have this value. And I wouldn't have wasted all your time if this wouldn't be the case in a minute. I will show you which experiments can be done that will show that that is equal to square root of 2. But these are not trivial experiments. So anyhow, at first we see that it looks like it cannot be equal to square root of 2. Cannot, because the only possible answers are 1 or minus 1, never square root of 2. Right? Right. Okay, so I started to ask myself, why didn't I get the answer square root of 2? And then I realized that if I do in the middle an experiment here, I do in the middle experiment when I try to measure sigma x plus sigma y. What does it mean that I try to measure here sigma x plus sigma y? Okay, this is the initial vector coming here. Final vector coming here, and here I do an experiment. I will take the experiment last any short time that I like, but it's important to think every experiment lasts some short time. So I want to make an experiment that measures sigma x plus sigma y. What does it mean? It means I have to take a magnetic field in the x plus y direction. So like in a Stern-Gerlach, I have to take an inhomogeneous magnetic field in the x plus y direction. But if I have a magnetic field in the x plus y direction, then the spin in the y direction precesses around it, and the spin in the x direction precesses about it. So both of them are not going to remain constant of motion. In fact, the magnetic field in the inhomogeneous direction is uncertain because of the position of the atom understand there are experiments as uncertain, I will have an uncertain rotation for both sigma x and sigma y. So very quickly, what I will measure here will not be the property of these two vectors because I destroyed them. When I have just a single vector, I can always find an experiment that does not destroy it. But I have two vectors like this. Every experiment will have at least, will destroy at least one of them, will make one of them rotate in an uncertain amount. So I then ask myself, is it possible to find new kind of gentle experiment, gentle, weak, gentle experiment, that I call now weak measurement. I gave it a name, weak measurement. In this kind of experiments, you come to each particle, you make an experiment that's very, very delicate. And with this kind of experiment, you can show that there is an interesting limit, that you don't destroy even one vector, one particle, and nevertheless you can collect enough of them and get new information. So this is the new idea of weak measurement that is now being, as I told you, measured in many, many different laboratories and give you completely new results, like this result of square root of 2, because we have learned to find a way to look at quantum systems in a gentle way that will not disturb them at all. So now I want to describe to you this new subject that I call weak measurement. And I invented them only because I wanted to see these two vectors here. And that led to a new thing. I think it's an important lesson. You see, people think when people learn quantum mechanics, many times they are told, look, you just have to learn how to use the formula and don't worry, the mathematics, don't worry about the interpretation because it will lead you astray. That's, for example, Feynman in his book said, anyone who will try to think really what quantum mechanics means will be completely lost, go down the drain. But I think it's very important to realize that a formalism by itself without interpretation is not enough, because you have to know what questions to ask the mathematics, the equation. And the equation can never tell you, Schrödinger equation will not never tell you what questions to ask it. You ask the question, then it will give you an answer. But in order to find interesting questions, interesting new experiments, interesting new phenomena, you have to have interpretation above the mathematics, meta-mathematics language. That's the interpretation, concept, the correct concept to think about the mathematics will lead you to interesting questions. If you don't have any interesting questions to ask the mathematics, it's like a computer that you don't tell it what to do. It will never be able to do for you something interesting. So interpretation is very important. As you see the lesson here, because I was trying to put a new interpretation, I was led to new kind of questions, and then this led to new experiments. Okay, so here's the idea of weak measurement. Suppose somebody gives you n spin half particles that he prepared all of them in the same direction. But it does not tell you in which direction they were prepared. Your task is to find in which direction they were prepared. In order to distinguish them prepared in this direction or some direction theta here, you have to have enough of them, because the scalar product of one like this and one like that is cosine theta. That scalar product is not zero. So you cannot distinguish between two vectors if you have just one of them. But if you have an ensemble, a huge large number, then cosine theta to the power n goes to 0. So therefore, if you have enough of them, the direction becomes a property. Like in ferromagnet, in the Earth, we measure the direction with the spin needle. In the how do you call this thing that lets you find the North Pole? Compass. The compass. The compass, how does it measure, of course, the direction of the spins of the magnetic field of the Earth? This is a well-defined property because you have many, many spins that are opposing in the same direction. The question is how are you going to find in which direction they are? Anyone has a suggestion? I've given you this collection of n spins. You have to find out in which direction they're pointing. How would you go about doing that? Well, the usual answer is the following. You take a subgroup of them and measure for all the subgroup the spin in each direction. You get some of them plus 1, some of them minus 1. If the subgroup is sufficiently large, you can find what is sigma x average. Right? Then for another subgroup, you measure sigma y for each one of them. Then you find sigma y average. Once you have this, you still have one ambiguity of the sign, so you measure also sigma z. You have the average of the three components, you know in which direction the spin is pointing. Right? Because you have the three components of the spin. But that experiment is a destructive experiment because all these particles that you took here, you collapse their states. You did not leave them unchanged. I claim that if you have n large enough, you can do an experiment that will tell you in which direction each one of them is pointing without disturbing even a single one. There is a very interesting limit that people have not noticed of measurement that becomes more and more delicate. The interaction with each particle becomes weaker and weaker, so at the limit, although you collect information, you don't disturb it at all. So it's a new limit where you can do experiments in quantum mechanics without disturbing any single system. And why is this? The reason is the following. If you have an experiment that interacts with each particle very weakly, you can show the following. If the interaction strength is epsilon, you can prove, when epsilon is very small, you can prove the disturbance probability goes at epsilon squared, but the information is collected as epsilon. So if epsilon is the order of 1 over n, you sum n of them, you get information, but the disturbance that goes 1 over n squared for each particle means that even not a single particle was disturbed. That means that the usual thing that people tell you, that it's impossible to find the reality of quantum systems without disturbing it, and therefore there is no reality because you have always to say that the property that you discover is also part of the experiment, the setup, that's what both said all the time. Both said, don't speak about properties of quantum systems, because the properties are dictated as much by what experiments that you're doing as by the state of the system. So there is no reality in the quantum domain. There is always a reality only in the interaction between the surrounding and the quantum system. But if this is correct, and this is correct, it means that when you have ensemble of particles, and you always need an ensemble to check the properties of quantum systems, you can check all the properties of quantum systems without disturbing even a single one. Let me prove it to you now. So in order to prove it, I first want to use a nice formula that will be useful for us, and the formula is the following. Suppose I have an operator A and a vector psi, an arbitrary Hilbert space. I know that I can always write this new vector, psi prime, this is the new vector. I can always write it as a sum A times psi plus B times an orthogonal state of psi. So this is a general theorem in Hilbert in vector space, any dimension. If you take a vector, you can always take a component of it in one direction and another component in some orthogonal direction. Okay? This is a theorem in geometry. I can also show that I can make this B real because I can change the phase of this in an arbitrary way, so B is going to be a real number. And the question is now, what is A and what is B? Very interesting thing, because it's a very general formula that I don't understand why it doesn't appear in any quantum book, because it's such a beautiful formula. Let me prove to you that A is equal to the thing that we usually call A average, and B is the thing that we usually call the uncertainty of A. General theorem. How do I prove it? I first take and multiply this formula from the side by psi. So we have psi, A psi, is equal to A times psi psi plus B times psi psi orthogonal. Now, psi psi orthogonal is equal to 0, and psi psi is equal to 1. And this is the thing that we usually call A average. But now it's It's a geometrical property. It's not a statistical property. This quantity we usually call A average is exactly going to be the component that multiplies this psi. Right? And now, so I already know that A is equal to A average. Now let me multiply the vector by itself. So I take the vector A psi and multiply it by itself. So I take this and multiply it by itself. Since psi and psi orthogonal are 0, this will give me A squared from this plus B squared. Right? I take A psi plus B psi orthogonal times A psi plus B psi orthogonal. So get A times A is A squared, psi times psi is 1, B times B, I have shown to you that I can make B real, so B times B is B squared, times psi orthogonal is also normalized. So it's A squared plus B squared, and the cross terms are 0 because psi and psi orthogonal are 0. Now this I can rewrite as psi, bring the A as an addition operator, bring it here, so it's psi A squared psi, and that is what we call usually the average of A squared. So this is the average of A squared, and this is equal to the square of the average of A, that's A squared plus B squared. So therefore B squared is equal to the average of the square of A minus the square of the average, and that's what we call delta, usually delta A squared, the uncertainty of A squared. So I have now a general formula that's beautiful. It's so general that tells you that if you take any operator in Hilbert space, multiply it by a vector psi, it gives you the average of A, so-called average of A in the state psi times psi, plus the uncertainty of A in the state psi times some orthogonal state of psi. I don't know which orthogonal, but it's some orthogonal state. Very nice formula. It's very important to notice here that A average and delta A here appears here as mathematical properties in Hilbert space and not as statistical properties, because I'm not talking about ensemble of measurements. I'm talking just about a single system. Yes?
I'm not sure I actually understand the this first step where you say that A psi.
Which one? This one?
No, the one immediately below that.
This one?
Yeah. Why can you always...
A times psi is equal to some vector.
Yep.
Now, let's look first in 2 dimensions. In 2 dimensions, if I have a vector, I can always write it as some coefficient times this, times some coefficient times that, okay? So I started with a vector in this direction, applied the operator A and rotate it to some other direction. I can always write it as a component here, but it's an orthogonal component.
Yeah.
Times some number. And that is true in general. Okay? That's explained to you? Any other questions? Okay? Beautiful formula. I'm surprised that it's not in every quantum book, CO book. Okay, now. Oh, okay. All right, now a general proof. Suppose I look now at an ensemble of particles. Psi total is a vector for an ensemble is equal to a product from 1 to n of the individual state psi of particle n is the product of n equal to 1 to n equal to n. I have n particles. All of them are described by the same vector, and this is the state of the ensemble. Okay? I have an ensemble of n particles that are all described in the same state. That means that I have a product of n vectors in different Hilbert spaces that are all the same, all right? This is an ensemble, physical ensemble. Now I want to prove the following theorem. If I define an operator A, I will call it A total. I define it to be as a sum of the operators of individual particles divided by the total N. For example, a particular case will be a sum of sigma x for all the particles divided by the total number. All right? That's the definition of a new operator. I have an individual operator for each particle. I define an operator for the ensemble, which is the sum of the individual operators divided by n. All right? I want to prove now a general theorem that in the limit when n goes to infinite, A total times psi total is equal exactly to A average for individual particles times psi total. So psi total becomes an exact eigenstate for every operator like this. So every operator that I write as a sum of an average for the n particles operator, at the limit when the number of particles in the ensemble goes to infinite, the ensemble becomes an eigenvector of this operator with the value which is the average for any one of them. Yes?
Okay, so this wave function that you've written shouldn't be confused with a many-body wave function, right? Because
well, it's a particular many-body wave function.
well,
which
you
is,
said that they're like each particle is in a different
you can have a special state of many-body particle that all the states are equal to each other. For example, in a ferromagnet, in the ground state, take a ferromagnet in the ground state.
Okay.
It's a special many-body example. Yeah.
Right. So those are distinguished by their site. So
for example, right.
There would be no statistics.
That's right. Yeah.
Like
They're
distinguishable.
You are distinguishable, and you can assume that they are non-interacting. You take them far away from each other and make a measurement on over them. Right. This is a physical ensemble. You can also make a physical ensemble in time. You take a single particle, continue to measure it again and again in a particular state,
right.
And then it will be an ensemble in time
yes.
of many repetition of the same
so
state.
So it's like another way of describing averaging.
That's right.
The expectation value.
Exactly.
Yeah.
No, but I want to prove now a theorem, mathematical theorem, that this is an exact theorem. Mm-hmm. That you can measure this thing without disturbing even a single particle. And still find all the information about the state. Without collapse at all. That's the new thing. People always thought that even in that case, you have to collapse at least some of the square root of n of the particle, something, not even one of them. So that's the new idea. Usually you think that when you measure some average, you can have fluctuations of the order of square root of n. That's not true here. No fluctuations at all. That's the new thing, okay? Any questions? Okay, so let me prove it to you. So I'm looking at the sum of an divided by n, x equals psi total. So let's take a particular one. Let's take the am divided by square root of n, and one of them, that one of them will, if I look at the ensemble, psi total is equal to psi of particle 1 times psi of particle 2, the same state, times psi of particle m times psi of the last particle n. Okay, this is the ensemble. Product of all the particles being in the same state, particle 1, particle 2, all of them being in the same state. Now, when I act with the particular operator am, it acts on the particle psi m only. And what does it do? It does exactly what I've proven before. Remember, I proven that A times psi is equal to A average times psi plus delta A times psi orthogonal. So when I look at the particular AM acting on this ensemble, it changes only this one and gives you two contributions. One of them is A average times the same psi total, because the A average does not change psi m. And then it gives you delta A plus delta A times the new state, that I will call it psi total M. The new state is the state where psi M was changed into an orthogonal one. Okay? So when I act with AM on the ensemble, I have A average that does not change the ensemble because it's A average times the same state, plus delta A times an orthogonal state for psi M, which is a new state here. Let me call it psi orthogonal total. It's orthogonal to psi original psi total, and it's orthogonal because the particle M went into orthogonal state. Right? You follow? Okay. Now the important thing is the psi. The important thing is the psi total, orthogonal M, and psi total, orthogonal N, and different from M, is equal to delta NM. Because if I change particle N to an orthogonal state, or instead I change particle M to an orthogonal state, I get the whole thing are orthogonal to each other. So therefore, I have here, when I look at the sum of AN times psi total, I have the following thing. I have A average times psi total. I get that N contribution divided by N here gives me 1. So I have got A times psi total, A average times total, plus delta A, delta psi total, where delta psi total is equal to the sum over N, delta A divided by N, of what I call psi orthogonal N. Now, if I look at delta psi total, absolute value square, I get something that goes to 0 as 1 over N. Why? Because these are all orthogonal to each other. So when I take this product with itself, I get simply N contributions divided by N squared times delta A squared. So the whole thing behaves as delta A squared, which is finite because it's an individual delta A, divided by N. So when N goes to infinite, that goes to 0. That means the size of delta psi goes to 0 when N goes to infinite, and that means that the sum of AN divided by N times psi total gives me exactly the value A average times psi total. I did not change one particle in the limit. The probability for change one particle, which is here, is 1 over N. So not even a single particle was changed, and nevertheless I got information, because I got information what is A average for individual particles. For example, if I would have done it with the N spins that I discussed with you before, if I would measure the sum of sigma x divided by N, I would get exactly the value of sigma x average without changing even a single particle. The probability to change even a single particle will go to 0 with 1 over N. So this is the new feature of quantum mechanics that people did miss. The fact that when you do a gentle experiment, what I call a weak measurement, and you do it on a sufficiently large number of particles, there is no disturbance at all. And you can find the reality there. Because once you don't disturb it, you find what is there. And you can measure A average and A prime and average for many, many different operators, and they don't disturb each other, so you can measure all of them. For example, if I have many particles that are described by the wave function psi of x, the Schrödinger wave, usually you think that in order to measure that wave function, you have to do experiment. You measure how many particles are in position 1, how many particles are in position 2. You do this when you have an ensemble. And the probability to find how many particles in position 1 is psi star psi x1, psi star psi x2, etc. And everybody knows that you do this measurement, you must disturb the particles. Now I'm telling you that if I have a large number of them, or I have an ensemble in time, which is the same thing, I can measure the projection operator pi of particular value x1. I can measure its average exactly without disturbing the system, as I've shown you. But the average of this is exactly psi star psi. So I can measure psi star psi without disturbing even a single particle. So suddenly, this wave function becomes a true, real property if you have enough replicas. A true, real property because you don't disturb it when you find it. You can find psi, you can find also the phase, and in fact, in nature, just a few weeks ago, I think 2 or 3 weeks ago, there was the first experiment that was measured psi in this new way by some people in the United States, in Rochester, I believe, and they've used this new method that I've advocated to make the measurement of psi the first time without disturbing a single particle. Okay? So far, no questions? Yes?
If you made a collective measurement,
Sorry?
if you made a collective measurement,
Yes.
all spins at once.
What do you mean collective measurement?
So if you could make a joint measurement on all of them.
Because that's what I'm doing. For example, in a ferromagnet, if you look at the magnetic field produced by a ferromagnet, it's a collective measurement because the magnetic field is the sum of all the spins, but on average, each one contributes very little, and therefore the interaction with each one of them is very small, and that's a collective measurement. Let me say something more important. All the experiments that are done in the classical limit on classical objects are really classical experiments because they are all weak measurements. For example, I see this table, or I see you. How do I see you? A photon comes, hits you, and comes back to my eye, and that's how I see some details of you. This photon has a wavelength that covers many, many atoms, because the wavelength is micron. Micron is 10 to the 3 atoms in every direction. So it covers a large number of atoms, and interacts very weakly with each one of them. So it doesn't disturb each atom at all, and give me information because it makes a weak measurement of you. So all the things that we see in the macroscopic level, in the classical level, are classical not because people always said that the classical objects are large or massive. That's not the reason. The reason is that all macroscopic objects are made of many, many quantum particles, and every time we interact with the macroscopic object, we do a measurement that interacts so weakly with each individual quantum particle that it doesn't disturb it, and nevertheless it corrects an average property that gives us all the macroscopic information. So macroscopic information are all averages over quantum-like ensembles. The ensembles are not exactly ensembles. For example, if I look at the position here, the position of this surface in this direction, there are many different particles in different locations, but in the y direction, they all have the same thing. For example, in a laser, when you have a mirror, the mirror and laser, all the photons see a mirror that has a definition of position much better than 10 to the minus 8 centimeter. The uncertainty in the position of each atom is 10 to the minus 8 centimeter, but the average position of the mirror is much, much better than 10 to the minus 8. Why? Because it's an average property. And the photon measures this average property without disturbing even a single individual atom. So that's all the classical limit is like that. Not classical limit is because you have a massive object. It's because each classical object is made of many, many atoms, and all the interaction that we do when we communicate classically is by using this kind of weak measurement. Yes?
So the only problem I'm having with this is I'm not sure that I understand the difference between the two statements, that this is a measurement over a large number of things compared to this is a large object. The statement.
No, because a large object can be a single particle that's very massive. There are two different things. You can have large mass because you have many light particles. You can have large mass because you have a single particle that's very heavy.
I see. So it's confusing because of
it's confusing. Yeah.
Anything that is large actually must be many particles.
No, I know. Must have many particles, but it depends what property you're looking at. If you look at the property of the center of mass, then indeed you behave like one massive object. Yeah. But if you look at the property like the magnetic field of n spin-half particles, it's actually built out of contribution of each spin-half. So it's an average of many, many particle spins. It's not a single object that acts like the whole mass of the thing. So there is a distinction between the two. So if I look at the position of this surface, it's not something that is like one single body. It's a collection of many atoms that are reflecting the photons. Each photon interacts with a large subgroup of them, and therefore it doesn't disturb any of them. It gives information not about the big mass. It gives information about something that is very delicate, the shape of the surface, all the things that we see. So this is a different way of going to the substrate limit.
Right. I mean, I agree. That is very striking. So, for instance, if you have a capacitor, you can measure the displacement, if you like, of the surface of one plate of the capacitor to some minute fraction of the size of an atom, and that's so okay. So it's just a
that's right. Yeah, it's the same idea.
Yeah. Okay.
But what is nice here is that there is a proof that you can do it without disturbing any one of them at the limit where the n is sufficiently large.
Right.
The probability of disturbing any one of them goes at 1 over n. And that's significant. That's why you can do it many, many experiments, classical experiments, without a collection, a description, a experiment that keeps going.
Right. Particularly in the capacitive measurement, you're doing it at such a low frequency that you couldn't conceivably disturb anything.
Yeah, and that means that it interacts so weakly with each one of the atoms and it collects information, average information from all of them. So this is a weak measurement, a special example of weak measurement. Yes?
So how does it connect to this square root of 2? I mean, when you have the
Okay. Yeah, I know. I have not come to the punchline yet. But good that you reminded me. But still, that was an interesting side thing, which is nice, right? In this direction, the digression. But now I come to the main new point. Okay, so. Let me use that device. What happened?
That's it. Keep going.
Huh? That's a new one.
You can keep going.
Yeah?
It's up there still.
Oh.
You can write
No, I was trying to get it
Right,
down.
but this is
Oh.
fine.
No, that's fine. Okay. Now comes the new question. I have shown to you that if I have a measuring device that interacts with n particles, very weakly from each one of them, it gives me from each one of them a contribution that the sum of the contributions divided by n gives me the average of A. Okay? The question now, what does the measuring device see when it looks at each individual one? Remember, the measuring device can be described as some pointer with some uncertainty. The fact that it interacts with very weakly with each one of them means that each one of them moves by very small amount of the order of 1 over n compared to its width. And only when you collect enough steps like this, you see something. Only if you collect enough shifts, you see something. So the question is whether the shift of the pointer by each step is equal to A average from each one of them, or from some of them it's equal to A1, and for some of them it's equal to A2. Suppose A is like a spin. Let's make concrete. I say I measure the sum of sigma xn divided by n, and I get sigma x average for each one of them. The question is now, the measuring device comes and first interacts with the first particle. So its pointer is shifted by what? It's shifted by sigma x over n, sigma x average over n, or it's shifted by plus 1 over n or minus 1 over n. These are two different possibilities, right? Maybe sometimes it's shifted by plus 1 and sometimes it's shifted by minus 1, so that altogether the shift is the average. That's what you would expect from a classical experiment. Or maybe each one of them shifts it by exactly sigma x average. These are two different possibilities. You understand the difference? Now I want to show you something very exciting. That the answer is not this and not that. The answer depends on what you do in the future. Which experiment you do in the past and in the future tells you how the measuring device is moving when it interacts with each one of them. So let me prove you that, and that is the new idea. So let me look at the following interesting formula. If I look at the average of A, I know if I write it, I can write it as psi, the operator A times psi. This is the average of A in the state psi. Now I do, again, a mathematical trick that leads to something very interesting. I put here a complete set of states, so I write here psi times a complete set of states phi n phi n times a psi. You know, this is a sum over n. You know that the sum over n of the projection operator phi n is equal to 1. You all know that theorem? If I take a complete set of vectors, sum of the projection operator, all of them, it gives me the value 1. If you don't know that, take it as a homework exercise to prove
I
it.
think Anna probably taught them. I think Anna actually taught them exactly that earlier this week.
Oh, okay, good. Because I saw some glazed eyes here. So you did not remember that. Okay. So far, so good. But now, I do a following trick. I write sum over n, psi phi n, and now I multiply here by phi n psi, and divide by phi n psi. I multiply and divide by that, assuming that all the phi n's are not orthogonal to psi. So this is one. I multiply and divide by the same thing, and then I have here phi n a psi, and I take this and put it here. Phi n psi.
So what happens if psi and psi n are orthogonal?
No, I just assume that this is a set of measure 0. You know, if you have a set of vectors, the chances that one of them is exactly giving 0 is a set of measure 0. Think about spin. They have continuous direction. As long as the direction is not exactly the same, you don't get 0. So this is a set of measure 0. So don't worry about things that are a set of measure 0. I can always avoid it by assuming that I have selected a set of states that none of them is orthogonal to psi. This is the general. The chance that this will not happen is a set of measure 0. Okay, now, why I'm interested in it? So far, you know that this is exactly equal to A average, right? That's what we have shown. But see what interpretation I can give to it. What is this? This is the probability of starting with psi and ending with phi n. Remember that my weak measurement does not change psi. So for each particle, I can say if I start with psi and end up with phi n, particular phi n, the probability for this particle to be in this pre- and post-selected ensemble is equal to this number. So this is let's call this the probability for particle n to be in the pre-selected. So probability for each particle to start with psi and end up with the same state phi n. This is probability. And then I see that the A average is equal to that probability multiplied by this funny number. So quantum mechanics is telling us something extremely exciting. It tells us that the average of A that you measure in ensemble can be thought about not only as the number of times you get an eigenvalue of A times how many times you got it, but instead to think about the number of times that you started with the same state psi and ended up with a particular phi n, the number of times like this gives you the probability to start with phi and getting phi n, and in the middle, when you measure this weakly A, you get a particular value which is equal to new thing. So this new thing I call A n weak. It's the weak value of A. Weak because they make a weak measurement. The weak value of A, if I start with the initial state psi, end up with the state phi n, is defined to be equal to phi n A psi divided by phi n psi. So I claim that it can be proven exactly, this is just a hint, but it can be proven exactly that if you do a weak measurement, namely if you have a measuring device that interacts weakly with a given particle, and this particle is pre-selected in the state psi, post-selected in the state phi n, you will get the value, when you measure the value A weak n. So in general, I have now two states, psi 1 and psi 2, or psi and phi, say. I just say psi and phi. This is pre-selection, post-selection, and assume the Hamiltonian is 0, so that the whole time is this and post-selection, otherwise I have to take into account the time evolution. So if I make a weak measurement of any operator A, starting with the state psi, ending in the state phi, I will get not one of the eigenvalues of A, not the usual average of A, but a new type of property. A new type of property, which is the weak value that is defined as phi A psi divided by phi psi. So in particular, if I know that A, the operator A, is equal to a sum of A1 plus A2, and psi is an eigenstate of A1 with the value A1 psi, and phi is the eigenvalue of A2, then A weak is equal to A1 plus A2. Why? If I look at phi times A1 plus A2 times psi divided by phi times psi, this is this A weak. Then A1 times psi will give me the number A1 times psi. A2 acting here will give me the number A2 times phi. So this will be equal to A1 plus A2 times phi psi divided by phi psi. So it's a general theorem that if I have two vectors, one of them is an eigenstate of one operator, and the other is the eigenstate of the other operator, and I do a weak measurement, I will find the sum of the two eigenvalues. So in particular, when we come back to that question, I started with an eigenstate of sigma x, and ended up with an eigenstate of sigma y. If I will do a weak measurement, I will find indeed the sum 2, or this divided by square root 2, the impossible sum. And how can it happen? It can happen because of interesting new type of interferences that, when I investigated them, I invented something that I call quantum random walk. It now is a very popular subject. To understand how is it possible that a measuring device will give you results that are completely outside the range of the eigenvalues. Okay? So that's the last thing I want to show you today, if I have time. And this is really only touching the subject, so I hope I whetted your appetite enough so that you can start to read some articles, because there's a huge number of articles now written about weak measurement, weak values that came out of this investigation. So let me, before I continue, any questions so far? By the way, when I give talks for the members, they can come also, right?
Yeah.
Oh, they're allowed to or not? Maybe not, I don't know.
They're allowed to, it's just because
but they have other things
the
that happen there.
schedule. What time's your talk?
It's 11 o'clock on Tuesday. There's something else, okay?
We'll see.
All right. Anyhow, you can find many, many articles about it now. All right, quantum random walk will be the last thing that will show to you how it's possible to get from sum of eigenvalues to get something that's completely outside of the eigenvalue range. And that's something connected to a subject called quantum random walk, and also another name for it, catching name, is super oscillation or super Fourier. You will see all of that now mathematically. So you see, just if you are interested in questions about intuition, you suddenly find new things in mathematics. And mathematicians are now interested in this new kind of formulas that are called super oscillation, super Fourier, that explains how from a sum of Fourier components up to given values, you get the Fourier component outside of this value. That's exactly what happened to the measuring device. Okay, so let me describe to you what I invented that I called quantum random walk. A classical random walk, you have a point, and you say, I throw a coin. If the coin comes one side, I take a step delta L in this direction. If it falls in the other side, the safe extension delta L in the other direction, okay? Say the probability is 1/2, so I have probability 1/2 goes this way, 1/2 goes that way. Suppose I throw the coin n times, I have a probability 1/2 to the power n to get all the time one side, because I'm interested in these extreme cases, and then the maximum distance I can go here is L, which is equal to n times delta L. This is the maximum distance I can go this way, and it grows down exponentially. Okay, I have a Poisson distribution. The usual spread is square root of n times delta L, but the extreme cases that I'm interested in, the maximum value can go classically is n times delta L. All right? I want to show you now that when I will invent a quantum extension of that thing, I can go much bigger distance than L. How is it possible? So how do I generalize to quantum mechanics? I first of all want to have a quantum coin. What is a good quantum coin? Of course, spin half. If I start the spin in the x direction, and then I say, if the spin in the z direction is +1, I will push the particle to the right. If the spin direction is -1, in the z direction is -1, I do an experiment like this, then I'm sure that I cannot cheat. Quantum particle does not cheat, because the probability is 1/2 that I will move in this direction, and 1/2 that I will move in this direction. So this is a good quantum coin. And then I want to generalize also the point to a quantum particle. So instead of having a point, I will have a wave packet. All right? So now, in a single quantum step, what can happen? I throw the coin, and I will move either in this direction or in this direction by delta L. To make this an interesting case quantum mechanically, I will make delta L very small, a single step very small compared to the step, to the uncertainty, so that I can have interferences between going to the right and going to the left. And lo and behold, if I do the right interference, then in a single step, I can go a much bigger distance than delta L. So that altogether, I will show you just by adding the probability, the amplitude to go in the opposite direction, I can make a much bigger distance. Very surprising. You would think that the largest distance will be, if you all the time pushes in that direction. No, quantum mechanically, if you interfere going in this direction, in that direction, then the interference can give you a bigger value. That's a big surprise. Let me prove it to you. But maybe I can show it to you intuitively first. Suppose I look at the Gaussian, e to the minus q squared, okay? And I make now a shift, that's q squared over 2. I make now a shift to e to the minus q, say, plus delta L squared over 2, okay? That's a shift to the left, actually, all right? If this is q, that's a shift. When you add delta L, you shift in the opposite direction, right? Because in order to get here 0, the maximum, you have to take q equal to minus delta L. So when you write here plus delta L, you shifted it by a distance delta L to the left, all right? Now, if delta L is very, very small compared to 2, to the uncertainty, or square root of 2, okay? Then you can expand this and write it as e to the minus, you can write it as e to the minus q squared over 2 times e to the minus q delta L, and then times something that you can neglect, right? Because the delta L squared is negligible. You're interested only in first order in delta L, right? So this you can write to first order as e to the minus q squared times 1 minus q delta L. You expand this to first order in delta L, all right? Okay? Now, suppose I say that I take an amplitude A times e to the minus q plus delta L squared over 2 plus another amplitude B times e to the minus q minus delta L squared over 2, okay? I superpose the state where I moved it to the right plus the state where I moved it to the left, or vice versa, the left and to the right. So using this formula, I think I get e to the minus q squared times a plus b that's from the 1, plus Q delta L times A minus B. All right? This is the first order. Agreed? Because here I move this by minus. This is by minus there, so that's comes with the opposite sign. So this can be rewritten as A plus B times e to the minus Q squared times 1 plus Q delta L, A minus B divided by A plus B. All right? And because this is small, I can rewrite it as A plus B, that's just an amplitude, doesn't depend on Q, e to the minus Q squared. The important thing that depends on Q is from here will be e to the Q delta L times the Q times the new number. I will call it delta L weak, where delta L weak, the weak shift, is equal to A minus B divided by A plus B. Right? Is this thing, the times delta L. Okay, so you see I can rewrite this now as a new shift due to the interference, which is equal to the old shift multiplied by A minus B divided by A plus B. Right? Now this can be much larger than 1. If I choose B to be nearly minus A, right, then this will be very, very small, and this will be finite. So I can get this to be a number large compared to 1, and as long as the whole thing is very small still compared to 1, because delta L was very, very small, this will be a good approximation. And I can get at each step a movement that's much bigger than the maximum movement I could do if I go on to the right side. Now this is in the very beginning of the whole idea of what happens in random walk. I don't want to spend more time on it. I gave you enough hints. If you're interested in it, open. There is a whole host of literature about it. You can read about quantum walk, about quantum weak measurement. I can just tell you what happens now in the experimental subject. Experiments have done over the world. All kind of, there is beautiful amplification that happens here. We've shown you amplification. There are experiments that are amplifying things that have not been seen before. Using weak measurement, you can get much bigger shifts of things. So you do weak measurement, you do pre and post selection, and then you get to see things that have not been seen before. As I told you, people now are able to measure the wave function weakly. There is something that's very well known that was invented by one of the people here, that Hardy, his name is Hardy, Yakir Hardy. There's something called the Hardy paradox, that people didn't understand what to think about it with this new way to think about quantum theory. I gave interpretation for it, which has been checked in Japan and here in Toronto. And there are many, many other experiments that are opening the way to new things. And there are also generalizations that are suggested by it, but I don't have time to talk about it now. I hope again that I whetted your appetite enough to try to read something about it. And I think that you got the lesson that if you worry about foundation questions, it's not just philosophy. It can lead to really new things in physics. Okay? Thank you.